Hi, we are continuing our discussion of chapter 5, the spatial design. As we mentioned earlier, the spatial design and this chapter discusses three main topics. First, principle of parallelism, principles of parallelism, and there we talked about the granularity, the degree of parallelism, and we talked about as well about spatial organization. In this lecture, we would like to talk about how to identify parallelism, and that for that purpose, we'll discuss ordering, something of discrete math, um, dependence, and we'll talk about uniform dependence vectors, uniform dependence vectors. The third topic, which we'll do on a later chapter, it is parallelism with FPGAs. Okay, so our main topic is identifying parallelism, which is the topic of this lecture. This is to tie the pieces together with those various parts of chapter 5. Okay, so let's talk about why do we need to identify parallelism? Why identify um, parallelism? Parallelism. Why? Um, well, spatial design, to explore it, you need to know the parallelism that exists in your design. Unfortunately, in our systems, we typically start with the software reference design. And the software reference design inherently sequential. This is a sequential. And what we want to do is we want uh, to go to a parallel implementation. But this jump is very hard and difficult in complex design. So what do we do then? What we do is that we have to go through intermediate step that makes it easier, and that step is the dependence graph. So from the software reference design, what we want to do is go to a dependence graph, which will make it easier for me to explore parallelism and go for parallel implementation to have the benefit of speeding up the design in spatial design. In an essence, really, what we are doing here is that you will see that in the level of abstraction. So if we have this is the abstraction. Our software reference design somewhere in the middle of this abstraction, and our parallel implementation, we have to do a lot of details, so it is lower in abstraction than the software reference design. However, to reach this, what we need to do, we need to do some kind of discover parallelism. We need to discover parallelism through dependence graph. Dependence dense graph. And from there, it is a lot easier to do some kind of synthesis to a parallel implementation. However, the going immediate from here to here is hard and difficult. So again, this is some kind of rewording of what we just stated, but we are using the abstraction scale here to illustrate the point. In other words, we are going higher in the level of abstraction to discover parallelism, okay, and then going lower to the parallel implementation, and that and use spatial design to speed up our design. Okay, all right. So let's go here for so um, let's talk a little bit about some discrete math. Oops, it's, did okay, some discrete math here. So let's talk about something we refer to as ordering in discrete math. And ordering is consists of a set S or T, whatever you want to call it, and some kind of a relation. Now, uh, ordering um, can be of different levels. We have we have legal ordering. I'm sorry, we have partial ordering, and we have total ordering. Now, the the partial ordering satisfy the following properties: reflexive, and that is the state. Um, okay, so let's assume here, for example, you have A, B, C. They all belong to the set S, and reflexive means that and let's pick the relationship to be, for example, less than or equal, for example. So the reflexive say that if for any element for any element a is less than or equal to itself, which is true. Okay, and the second property is anti-symmetric, and that is basically if A less than B and B less than C, so that means and B less than, I'm sorry, A, that means A equals to B. Okay, and then um, finally, um, the transitive property, which says that if A less than or equal B and B less than or equal C, then this A is less than or equal C. Now you add one more property, okay, which is property 4, that makes it total ordering. Okay, so you remember the partial just satisfies these three. The partial satisfies these three. You add the fourth one, becomes a total ordering, and the fourth one is the comparability. And basically, it says that for any A or B, either A less than or equal B or B less than or equal C. It establishes an order, a complete order. It establishes a complete order. Okay, so let's take a quick example here, and we'll say that, uh, um, let's say, for example, here you have um, Here, in this graph, I have 1 less than the number above it, which is 2, less than the number above it, which is 3, less than the number, the integer above it, which is 4. So this is a total ordering, as I defined it like so. Partial ordering, if I say something that A um, um, uh, comes before B and it comes before C, and both of those come before D. For instance, if I define this relationship, then this is a partial ordering. Notice I did not state a relationship between the order of B and C, so that's why it's partial. Your textbook refers to something as legal order, excuse me, and, and says that if we reorder the instructions of the program in a different way and we get with the same results at the total order, then it is a legal order. I guess it is more of restating the partial order in one way or another, but we'll take it from your textbook. Okay, so our goal here really in this whole discussion is we want to convert the total order by the software reference design defined by the relationship comes before, the instruction comes before, to a partial order which defines the relationship that says must execute before. And there is a difference between the two of them, by the way. Okay, and this is where I discover parallelism. Okay, all right, so this is our goal right here. Okay, okay, so let's see here, for example, let's see, let's go back to the lecture slides here and take and okay, so here in your lecture slides, you have this example where he says we have a small code here, which is let's see, three statements. Statement one, what it does, it adds x and y and produces a. And statement two, it subtracts x and y and produces b. And statement three, it uses both of results, all right, of the previous two statements to compute r. Now, obviously, a total order here, if you want a total order which defines the statements as they come, we say that a total order equals, okay, statement one, then statement two, then statement three. Why they are ordered here? Because we are ordering as they are in the code. That's it. But we can find a legal order where we get the same result by, for example, switching S1 and S2. Notice that S1 and S2 and they are dependent only on X and Y. So we can have another legal order here where it says, you know what, I could have S2 before S1. What's the problem? Okay, but both are producing a result that S3 needs, so S3 has to stay then. So we call T prime a legal order. I can define partitioning order by saying that S1 must come before S3 and S2 must come before S3. No specific order between S1 and S2 because they are really not dependent on each other. So you can see that the legal and partial sort of they complement each other. They don't really, but they are completely different from the total ordering. The total ordering depends on how the instructions are ordered in the code. But the legal order says, how can I reorder the instructions in such a way that I will get the same results? Okay. Now, so this brings us to the relation of dependence. And the relation of dependence really it defines basically the instructions that exists in my set T, and I'm going to assume that set T is my program. And basically, what I want, you can see that the instructions in the program appear one after another. If I take the relation comes before, then I will establish the relationship between these, and I will order them as they appear. Instruction T1, then T2, T3, etc. as they appear. This is my total order. But this total order is imposing unnecessary sequentiality, and I can change this relationship from comes before to another relationship that says must complete before. So if I can think of this changing of the relationship, then I will change the total order to a a sort of partial order, partial, partial, or as your textbook referred to it, legally partial order, and that order will help me discover parallelism. So we are changing the relationship between instruction from comes before, which means as they listed in the code, to must complete before, which means a true dependency. Now, so now this is really an interesting, because now with this must complete, the relationship becomes as follows. If instruction I produces a result to instruction J, then we say that they are, see, this is the output here, this is output, and it's an input here. So we say that a true dependence between two instructions, so instruction tj depends on instruction ti if the output of instruction ti intersect with the set of input for instruction tj, and that intersection is not zero, meaning there is an element, one or more, that is produces by this, and let's change color here. So there is an element that produces by this instruction ti, and it is needed by instruction tj. And if that is true, okay, and if this set is not empty, then we say that instruction Tj depends on instruction Ti, and this becomes part of the dependence relationship. Okay. There are other, so what we just described is referred to as true dependence. There are other dependence that we have covered in computer architecture class. One of them is output dependence. And notice that here, for instance, in these statements where we are adding x and y, saving it to a, and a is copied to r, and we subtract x and y and saving it to a, and r divided by b, 7 to R. So now notice that, say here in this case we say that this 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 instruction writes to A, and this instruction write to A. Okay, so what we say here is that there is an output dependence. This instruction S4 must complete by before S6, and this S6 is the latter instruction. So that's an output dependence, or what is now what we have, what we refer to as, yeah, NT dependence. Okay, And notice that A is being read by this instruction. Okay, so which is R. Let's change color here so that we can. So um, R. I'm sorry, A is being read by this instruction. Okay, and so there is a dependence here. Okay, where we say that so we say that A has to be used by this instruction before it is written by this instruction. Okay, all right. So this is called anti-dependence, and this is typically resolved by renaming. All of these are easy ones. The output dependence can be resolved by techniques either by the programmer or the compiler, mostly the compiler. But the true dependence are the tough one, which determines my parallelism. But so we are mentioning the output dependence and anti-dependence as matter of completeness, since we are discussing the dependence. Okay. Okay. Okay, so now we go back to our three statements, S1, S2, and S3. And our goal is to establish this dependence relationship, this dependence graph. How do we do it? For every instruction, we list the inputs. So instruction 1, the inputs are X and Y. S1 inputs are X and Y, and the output is A. S2 inputs are X and Y, and the output is B. And S3, the output is the inputs are A and B, and the output is R. And now I kind of list this table where I have the output of the instructions, the output for S1 and S2 and S3, and the input for instruction S1, instruction S2, and S3, and I will try to do intersection. So, for instance, the intersection between input for S3 and the output for S1, okay, is A. So the input for S3 and the output. So you can see this output from S3 goes and becomes an input to S3. Okay, you fill up this table and you can see that clearly you have here this A and B. All of the rest are empty. So that basically established for me this relationship where it says that statement S1 and S2 provide data to S3. So S3 is dependent on S1 and S3 is dependent on S2. Clearly there is no relationship between S1 and S2, and clearly I can execute those on parallel, but I cannot execute S3 in parallel to S1 or S3 in parallel to S2. So you can see this boundary of parallelism start to appear in my dependence relation, and the relation can be established as S3 depends on S1 and S3 depends on S2, and I can write it as such or represent it in a graph as such. Sometimes a parallelism can be discovered very easy in HDL constructs. So for example, if you have an if statement here, if there is a condition, then S0, if else S1, this S0 and S1 very clearly they can be executed in parallel. Also, when we execute loops, right? When we execute loops, it is very well known that you can unroll the loop and explore parallelism. Unroll the loop. So these are very very easy tricks. Sometimes induction variables. So in this case, we are using J and K, and we are imposing really dependency on ourselves. But if we just remove those J and K, and we are clever enough by just initializing two variables here, or two, KII2 and KII1, right? And let just the only variable here is I in the loop, and that way I would limit uh, those extra variables inside the loop, and it will limit the extra fake dependencies that I have in my loop. So really the true variable inside here this loop is the I becomes, and makes it easier to discover further dependencies and parallelism. Okay, so the final topic here is dependence vectors, uniform dependence vectors. And basically, the what we are discussing here is that whenever I have a loop, um, let's say 10 I plus plus, and we're trying to discover the parallelism within the body of this loop. If there is if the dependence is let's say contained or limited within the iteration, we say it's a loop independent dependence because it is within the iteration. However, if between iterations I have dependence, so then we say loop carried dependence because this is becomes between the iterations, and we'll see examples for that. So we'll talk about loop independent dependence and loop carried dependence. All depends on how you carry the dependence within the iterations or between iterations. So let's start with loop independent dependence, which means the dependency is within the iteration itself. So take a look at this loop, for example. We are basically multiplying an array of x elements with a constant and saving it in the array A. There is within every iteration there is a dependence. Obviously, the AI provides the results to xi. Okay, so but with this is within the loop. We can represent this in the iteration space as follows. We say that we have iteration. This is now iteration space. This is this here axis is the iteration space. We say that iteration 0 has no influence on iteration 1, no influence on iteration 2, no influence, etc. Okay, so everyone is independent. If you have doubly nested loops here in this case, okay, again, what we are trying to do here, we have an array of let's see, we have an array xij, okay. So we have an array here of xi, array X and array A. And what we are doing, we're doing some simple manipulation here of math, but notice it is limited within the inner loop here. So we have the inner loop and the outer loop, and you can see that we can represent this um, in the loop iteration space. So this is the loop iteration space, okay, and the inner loop here I index and the j is the outer loop, and you can see here that every row here every row represent outer loop, and those represent the inner loops. Okay, so you can see inner loop, inner loop, inner loop, inner loop, inner loop, and then outer loop, outer loop, outer loop. And these connected dots, we do not have something like this because every iteration is limited in the dependency within the iteration. There is no there is no between iterations dependency. We don't have loop carried dependence. Okay, so let's go to loop carried dependence, which means dependence between loops. And see here, for example, here, when we are doing a summation of an entire loop, and we can see that this is sum from I 0 equal to 10, and we are doing the sum. And so obviously, iteration 0 provides the result for iteration 1, which provide the result for iteration 2. You can see these arrows now. Those arrows now start to appear, and those arrows tells you that you cannot really parallelize those. We do parallelize them later on, but it appears you cannot, so because of the dependence that you have. Similarly, in this loop, you can see here you have two nested loops here. You can see that within the inner loop here, uh, um, uh, you have some kind of dependence. Okay, so within the inner loop, right? But the outer loop. So this is the outer loop, and this is the inner loop. The inner loop you cannot do dependence, but the outer loop you can do dependence. So in this case, what we can tell is that if you can have three parallel adders, every adder of those can work on, let's say, loop I equals 0, loop I equal 2, and loop I equal 1, loop I equal 2, and loop I equal 3, and they can work in parallel because there is no dependence between the outer loops, but there is a dependence within the inner loop. Okay. Okay. So with this slide, uh, uh, we have completed our discussion of um, uh, the identify parallelism, where we talked about ordering, dependence, and uniform dependence vectors. Thank you very much. We'll see you in the next lecture.